Hello and welcome to Lecture 30 of Math 2R03. In today's lecture, we're going to finish up looking at Section 6b in the textbook. In particular, we're going to look at linear functionals. And the other thing I want to do is kind of look at some of the material in 6b and do a kind of a worked out example. So that's kind of our goal for today. And our starting point here is the observation that if you take f, where f is the real numbers or the complex numbers, that it's also an example of an f vector space. Right? So for any vector space V, the set of all linear maps from V to F makes sense because we can think of F as a vector space. So we're looking at all maps from your vector space V to the set F. So this makes sense. And what we want to do today is kind of look at elements inside of this set. So, uh, so we want to give a special name to these objects. And we just say a linear functional of V is any element of this set of linear maps from V to F. So when I say linear functional, I just mean a linear map. And the difference is that I know exactly where it's being mapped to. So that's one way to think about what a linear functional is. And let me just give you an example. Let's say our vector space is F3, so all triples with entries inside of F, and we define a map from this vector space V to F by just taking any triple x, y, z, and we map it to 3 times the first coordinate plus 12 times the second coordinate minus 2 times the last coordinate. Okay, so this would be an example of a linear function. You can check that it has all the properties of a linear map. But now what we want to do is make an observation that if we kind of let this symbol here denote the standard Euclidean inner product on F3, then we know that our function, our linear function, which takes x, y, z, and we map it to 3x plus 12y minus 2z, notice that that's the same thing as taking the triple x, y, and z, and you're doing the standard inner product with the pair 3, 12, minus 2. Right? So if I had said use the standard inner product on this pair, triple and this pair, you would output this element on in the middle. So what we have here is a linear functional agreeing with some sort of inner product. So this is kind of fixed, and as we let x and y and z vary over all triples, and we fix the second coordinate of our the second term of our inner product, we're getting something that agrees with our function. Okay, so you may think that this is kind of a one-off. Let's do another example. So let's say we have our vector space of all polynomials of degree 2 or less, and we're going to define a linear functional on this space by taking any polynomial, and we're going to map it to the number that we get after we integrate this polynomial on the interval, closed interval from 1 to 0. So this is taking a polynomial and we're getting a number, right? We're getting a number here. And I noticed I did something wrong here. This should just be R, right? Because we're mapping it to the set of real numbers. Okay. So that is an example of a linear functional. And so in general, if I take an arbitrary polynomial, we know from calculus what we're doing is we're integrating a0 plus a1 times x plus a2 times x squared dx. And this, using kind of first year calculus, this is equal to a0x plus a1x squared over 2 plus a2x cubed over 3 from 1 to 0. And when you plug that in, you're getting the number a0, a1 over 2 plus a2 over 3. So this is how I take any polynomial and I map it to a particular number, a real number. But notice that we can define an inner product on this space by saying, well, let's take two pairs, px and qx, and I can map it to the number 0, 1, or integrating from 0 to 1, by integrating the polynomial px times qx and dx, and then evaluating it at these endpoints, 0 to 1. So if you stare at this for a second, our function here, which takes our polynomial px and evaluates it from 1 to 0, is the same thing as taking the polynomial px and using the inner product over here where the q is 1. right? Because both this was the same thing as 0 to 1 px times 1 dx. So here we have another example of a linear function is somehow there's a fixed element that I can rewrite my linear functional as an inner product where the second element is fixed. Okay, now you may think, okay, that's very nice. Yeah, I've taken some nice examples where I can do that, but this actually turns out to be a much more general theorem. Okay, I think this is a very remarkable theorem, which says that let's say you have a vector space that's a finite dimensional inner product space. If phi is a linear functional, right, so that just means that it's a linear map from V to F, then there actually exists a unique element U in V such that this linear functional, okay, when you plug in V, it's the same thing as saying that take V and apply the inner product with this fixed U for all all U, V in V. So the Riesz representation theorem is saying if you're in an inner product space and you're looking at special linear maps, those linear maps are actually examples of linear inner products, okay, with a fixed second entry. So we're going to come back after the break here and we're going to prove the Riesz representation theorem.